Okay, thank you very much. It's a pleasure to be here. What time do I go to? Okay, great. So I'd like to begin by wishing Stephen a happy birthday. It's been a pleasure and an inspiration to be your colleague, collaborator, and friend for the last 35 years. And also, I would like to wish you many happy returns. Our work is not done. We can't stop here, and so we'll keep on going. So in the last few years, there's been a series of developing insights in the relationship into different kinds of long-distance infrared phenomena relating the gravitational memory effect, which we heard about from Gary, asymptotic symmetries, and the so-called soft theorems in quantum field theory. I spoke about this in this room last year. I'm not going to try to review this whole story now, but I am going to discuss one self-contained corner of it. So the minute you say the word infrared phenomena to a quantum field theorist, the first thing that they think of are the so-called infrared divergences that are encountered in computations of Feynman diagrams, in all physical scattering processes in quantum electrodynamics, in quantum chromodynamics, or in gravity. And the problem of the so-called ultraviolet divergences, which was solved by renormalization and Nobel Prize awarded to Feynman, Tominaga, and Schwinger, that is a separate problem. It also happens when you start to compute loop diagrams that you get infrared divergences. And this was first noticed in work of really Bloch and Nordzik in the 30s. People really didn't understand. Very complicated problem, decades of work on it, thousands of papers, textbooks, so on and so forth. And finally, the problem came to some kind of closure in a very famous theorem of Kinoshita, Lee, and Naumburg in the early 60s. And what they said is, we don't want to compute the S matrix. We don't want to compute amplitudes. We only want to compute probabilities. And the reason that we only want to compute probabilities is that real detectors have a finite resolution, and very infrared photons or gravitons or whatever will escape their detector. So S matrix are unphysical, only probabilities are real. And it was shown that, and there was great agreement with experiment, and this work was, I think correctly, greatly applauded throughout the particle theory community. And it's interesting that in marked contrast when 10 years later, when Stephen came along and said, we don't want to compute amplitudes, we only want to compute probabilities, the world went into an uproar and said that's completely outrageous, even though the same words had been accepted 10 years earlier in quantum electrodynamics. Now, these reasons for saying that you only want to compute probabilities and not amplitudes sound rather different, but I hope by the end of the talk, I'm going to circle around various things, and I hope by the end of the talk that you're going to see that they may actually be practically the same thing. So we've been discussing new ways of thinking about infrared structure in gauge theory and gravity. And so a natural question is, do these recent developments shed any light on this old problem of infrared divergences in quantum electrodynamics and in quantum chromodynamics? And obviously the answer is yes, or I wouldn't be talking about it. And this talk is going to be a compendium of different results from different papers, but the main collaborators are Dan Capets, Stephen Hawking, Malcolm Perry, Anna Riclario, and Sasha Zhiboedov. Okay, so what I'm going to do is I'm going to talk about, give a discussion of infrared divergences in QED, which has a parallel in quantum gravity. And I'm going to rederive some rather, I'm going to come to some conclusion about how to deal with the infrared divergences, which looks sort of amazing and new and remarkable, except that it was already discovered 47 years ago by Fadeev and Kulish. And so, but I'm just going to give a rather different way of thinking about some very old work and tying this all together. But I think of a more physical way of thinking about it. And that physical way of thinking about it is going to motivate three conjectures, which I'll make. One on quantum electrodynamics, one on non-abelian gauge theory, and one on black hole information. So let me give here a lightning overview of some of the recent discussions in quantum electrodynamics. Now, you're all familiar with the statement that in a abelian gauge theory, the global charge is always conserved. The sum of the incoming charges is equal to the sum of the outgoing charges. But what has been more recently understood that this is only one in an infinite family of conserved charges. And let me describe what these conserved charges are. And this is going to be a quick review of something which I've sometimes given whole lectures on. So here's a picture of Minkowski space. In the future, at null infinity, we'll use retarded time u, advanced time at past null infinity v, and the celestial sphere at null infinity will use the coordinates z and z bar. And here is scri plus, where light rays go to, scri minus, where they come from. And we'll also be interested in the past of scri plus, which is not scri plus minus, and that has to be carefully distinguished from the future of scri minus, which we call scri minus plus. And the statement is that if we look at the radial component of the electric field on the sphere at the bottom of scri plus, that is equal to, antipodally, it's not equal to it at the same point, that it's antipodally equal to the radial component of the electric field at the future of scri minus. And this can be thought of really as a boundary condition which defines the scattering problem, which is needed to define the scattering problem in Minkowski space. And this antipodal business may sound a little bit funny. I'm not going to have a long discussion of it now, but it is implicit in every problem in Jackson and every quantum field theory computation. It would not be Lorentz invariant without this antipodal identification. And was undoubtedly in some form known to Maxwell and Leonard and Vikar. Now, this looks a little bit trivial, but it suddenly starts to look, this, by the way, is one identity for every point on the sphere, and it's a conservation law. It's an incoming thing that equals an outgoing thing in any scattering process. Starts to look more non-trivial if we integrate by parts and along a null generator of scri plus, and then we can write this charge and use the constraints to integrate by parts. We can write it as the integral along a generator of scri plus of the divergence of the radiative component of the electromagnetic field plus whatever hard charges we can imagine here that we could have massless charged particles which go through scri plus. And in fact, in all of this talk, just to simplify things, I'm going to assume that all charges go through scri plus. We could also consider massive particles that go through time-like infinity, but that there's a very beautiful story there, but it substantially lengthens the discussion. So I'm just going to talk about charges going through null infinity. Now the so-called soft charge, if we work in a u equals 0 gauge, is a total u derivative, and it's related to the shift in AZ, which if space is flat, if the electromagnetic field vanishes in the far past and the far future, this soft charge measures the shift in the flat connection on the sphere at infinity, and these in turn label the infinity of degenerate vacua in Abelian gauge theory. So this soft charge is related to the shift in degenerate vacua, which is the electromagnetic analog of the memory effect that we just heard Gary describing a few minutes ago. And there's a similar story on scry minus. And the statement that Q plus equals Q minus is not only true in classical electromagnetism, but it's an exact statement in any quantum theory with an Abelian gauge symmetry, and it's known as the soft photon theorem. Okay, so that's a lightning review of that. Now let's apply our knowledge of this conservation law, and let's apply it to something insanely simple, which is just Bhabha scattering. E plus E minus goes to E plus E minus. There's supposed to be another H there. Now, of course, we can't just have electrons, again, I'm making them massless, and positrons going to infinity, because we have to solve the Maxwell constraint equations. And we're assuming that there are no incoming radiative modes, no photons. So here I've written the constraint equation on scry plus. And there's no incoming radiative modes. So I'm setting these modes to 0. And so the constraint equation tells me that the u derivative of the radial component of the electric field on scry plus must equal the flux of the charge current through scry plus. So now if we set the fields, the Coulomb field to 0 up here and down here, and we integrate, we'll find that we'll get some non-zero radial electric field here and here. And similarly, setting it to 0 up here, we'll get non-zero here and here. But they will not antipodally match unless the scattering is trivial. If the scattering is trivial and forward scattering, they antipodally match, and everything is OK. And so since they don't obey this matching condition, Bhabha scattering is identically 0. The quantum amplitude to scatter an electron and a positron and get out an electron and a positron is identically 0. That is implied by this conservation law. Now, in fact, this result has been known for a long time, but it is stated in a rather different way. And here's how it's usually stated. You start out, you do some computation, but then you have to have these diagrams where you exchange photons between external legs. And these diagrams have infrared divergences in them. And they're become infrared divergence when the energy of this photon becomes very low. And in quantum field theory, anything with very low or 0 energy is called soft. So when this photon becomes soft, this loop integral of the momenta around here diverges, and this diagram is actually infinite. But that's not the end of the story. There's a next diagram, which is infinity squared, and this has been analyzed in a very rigorous way. That's what Kenosha, Lee, and Naunberg famously proved. One of the things they famously proved. And you add the whole thing up, and you get e to the minus infinity, which is 0. So what I want to say here is that these infrared divergences is just the penalty that quantum field theory extracts on us if we try to compute something whose amplitude, we try to compute something that is violating a conservation law. So I would say there are no real infrared divergences in quantum electrodynamics. They are just there to set things to zero that we shouldn't, when we try to compute something we shouldn't have been computing in the first place. Now, it's not very impressive just to compute zero. We want to compute something non-zero. We know something is non-zero, so what could be non-zero? So the problem was that we had these Coulomb fields that were going down to the bottom of scri minus and the top of scri plus, and they weren't matching. So let's shield them, and in fact, let's solve the constraint equation not using the Coulomb field at all, but let's solve it using the radiative piece. Of course, there are many things you could do in between. You could have some Coulomb piece and some radiative piece, but I'm discussing the other extreme where there's only a radiative piece. So the radiative solution of this equation, I'm imagining that I have a particle that comes out to scri plus at retarded time u0 at the point z0 on the sphere. I can solve this equation for the radiative field az, and a number of interesting features of it. One is, except at u equals u0, it's pure gauge. And it has a step function in it. So there's a shift. It's a different pure gauge at plus infinity than it is at minus infinity. That's the vacuum shift I was talking about. And moreover, if we take its Fourier transform in retarded time, we get a pole. We get a soft pole as omega goes to 0. Now, we can also, this is a classical solution of the constraint equation, but we can also make a dressed coherent state which is annihilated by the constraint equation without adding the Coulomb piece, promoted to operators. And what we've done here is shielded the Coulomb field. Now, of course, we can't shield the zero mode of the Coulomb field with photons, but we've got E plus E minus here, so the net charge is 0. And when the net charge is 0, there are long-range 1 over r squared terms in E. They are not spherically symmetric. And what we would be doing here is shielding. So since the whole state is neutral, we can shield the entire Coulomb field. And then the matching condition is trivially satisfied. And since the matching condition is trivially satisfied, there's no reason the amplitude should vanish. And indeed, it's known that the scattering of these dress states that I just wrote down is in fact infrared finite. And this was shown in a way that it's rather hard to see that it's equivalent to what I just said, because the language that is used in 1970 and so on, that they're not talking about null infinity. The language that's used is very different. But Fadeev-Kulosh wrote down some dress states that have the property that the long-range Coulomb field is shielded, and showed, and the proof was improved over the years, and there was also Chung and Kibble. They showed that scattering amplitudes of these states are infrared finite. And what happens is this exchange, every particle now is surrounded by a Coulomb cloud, and the exchange diagram between external charged particles, which has an infrared divergence, is canceled by an exchange diagram in which the external leg exchanges a soft photon with the cloud of the same particle. And that cancellation is possible because this cloud has an explicit pole as omega goes to 0. Okay, so there are these obscure but somewhat studied infrared finite scattering states. And what we've constructed is equivalent from those, so we don't have to do a lot of hard work to show that this gives us something which is infrared finite. Now, one thing I want to say here is that these clouds don't really, I mean, I've drawn it in this way, but they don't really surround the asymptotic hard particle. Indeed, if it's a massive particle like an electron, that will go to time-like infinity, whereas the soft photons will disperse out to null infinity. Okay, so what I've done is just recovered from a modern viewpoint a way of thinking about infrared divergences and thinking about how you actually can have an S matrix in quantum electrodynamics, despite the appearances of infrared divergences at intermediate stages in the calculation. Now let me go on to the conjectures. So, Faddeev-Coolidge states, not all states are Faddeev-Coolidge states. And in fact, Faddeev-Coolidge states are highly unphysical. When we do an experiment at the LHC, we do not scatter Faddeev-Coolidge states. In order to do that, every time we set in a pair of protons, we would have to follow it up by a cloud of radiative photons whose distribution was tuned in just such a way as to cancel the long-range Coulomb field. Obviously, we never do that. So, however, so the conjecture is that you can move the cloud from the incoming state, the soft cloud, from the incoming state to the outgoing state, and one can show, I won't go through the discussion, that if you move the cloud in the right way, that this cancellation of infinities in diagrams still occurs. And indeed, if we move all the clouds to the final state, then they have the very natural interpretation as just the soft particles. We take a bunch of undressed charged particles and we scatter them, and there's a bunch of soft particles that the conservation law forces us to produce in the scattering process. And we've actually, this conjecture is actually rather easy to verify for the leading infrared divergences. To get into the details of the multi-loop diagrams and make sure there's no divergent subdiagram will be some work, but I think that should be doable. Okay, what about non-abelian gauge theory? Non-abelian gauge theory, there is no analog of the Faddeev-Coolidge proposal. The intricacies of the non-abelian structure in non-abelian gauge theory have, the Faddeev-Coolidge arrived at their state in a way that at least now seems extremely indirect. And it was too hard to follow their steps for the non-abelian case, despite many efforts to do it. So the status now is that there is no even a proposal for a construction of an S matrix for non-abelian gauge theory. And this is an important problem because there's a whole conference, which I'm going to next week, called Amplitudes, in which people study scattering amplitudes for non-abelian gauge theories, but there's no proposal for how they might exist because of these infrared divergences. So the conjecture is ditto, that as long as you satisfy the conservation law that from the incoming and the outgoing states, that the infrared divergences will cancel. Now gravity, it turns out, is simpler than non-abelian gauge theory and as far as the structure of infrared divergences. And there was a claim in the last few years that an analog of the Coolidge construction indeed exists for gravity. Okay, so now let me move on to the third conjecture for black hole information. So let's imagine that we make a black hole collapsing some classical matter. It forms and then evaporates. And it evaporates at the Hawking temperature, 1 over 8 pi gm. And the number distribution of the quanta of energy omega obey the Boltzmann distribution, omega squared over this factor. And this distribution goes to 0 as omega goes to 0. Certainly doesn't have a pole. So this distribution, we can think of these all as hard quanta. We aren't producing copious numbers of soft quanta, and they're hard where the hard energy scale is the 1 over the length of the radius of the black hole. Now, Hawking proposed in 1975 that this in-state coming in here will evolve to a mixed state, which where we have a sum over all hard states. I don't want to get into too much detail about what these are, but they're essentially the states that you would get from a black body radiating at this temperature for some time until it disappears, and with some probabilities that are essentially thermal probability distribution functions. Now, a few years later, 5 years later, Don Page came along and said, I don't like that. I want information to be, I want unitarity. I want information to be preserved. And so I'm going to conjecture that instead what happens is the in-state goes to some pure out-state where the C alphas would depend on the details of what was thrown in, and the H alphas are some typical element of a hard state consisting of hard quantita that appears in the probabilistic calculation that Stephen did. And moreover, that quantum purity, and we heard a little bit about this in Douglas's talk, that quantum purity is restored if we were to look at such an evaporation process by correlations between the hard quanta which emerge at early times and the hard quanta which emerge at late times. In other words, for the first half of the evaporation process, everything looks thermal, but in the second half, the quanta which come out somehow know about the quanta that came in, and the whole thing is a pure state. This is impossible, and it's impossible for the same reason that this can't happen, because it violates the conservation law. It's impossible for the same reason that E plus E minus cannot scatter to E plus E minus. We must have soft quanta produced in any kind of evaporation process like this. So I'm going to propose, now, I'm going to propose an alternative to Page's conjecture in which the in-state goes into an out-state where we have also this, which is now a sum of product states, where every hard state is appropriately dressed with some soft quanta. So Don didn't give any prescription or algorithm for how you compute these C's. He didn't say firewall or fuzzball or whatever. He just said there should be some mechanism so that this is happening. And similarly, I'm not proposing any prescription here. I'm just putting this forth as an alternative to what Page was saying. And now I'm making a second conjecture that the soft states are orthogonal. That is, the soft state associated with any hard state is unique. And if you do that, if you look at an inclusive cross-section, if you have a detector that can't observe the soft quanta, you must trace over the soft state. And then you get back exactly the Hawking formula if this C alpha is equal to the square root of Stevens rho alpha up to a phase. So in this correlation, so in this conjecture, a person equipped with a detector that cannot see the soft quanta will think that Stephen got it exactly right. And in order to see that there is a unitary evaporation process, one will need to measure the soft quanta. So this is a kind of minimal deviation, which is consistent with unitarity, but is very close to what Stephen was originally proposing. And the quantum purity here is restored not by late and early hard quanta, but by hard quanta and soft quanta. Now, could it be true that these S's are orthogonal? I think I won't go through the argument here. I won't go through the details of this argument, but I look at it in a theory of in which all the initial and final quanta are gravitons, and using super translation charge conservation, which is, so in electromagnetism we had all these charge conservation laws from the matching of the radial component of the electric field. In gravity, we have analogous infinity of charge of conservation laws from the matching of the Bondi mass aspect. That is super translation charge conservation. And then we have a second infinity from the matching of the angular momentum mass aspect. That is super rotation charge conservation. And you need both of those to decohere, to fully decohere, for the soft quanta to fully decohere the hard gravitons. And then in that case, tracing over the soft quanta fully decoheres the hard ones. And a very similar conclusion was reached in a beautiful paper last week by Carey, Carney, and Semenoff, and other and a few other people, in which they looked just really at a generic scattering process and showed that in a generic scattering process of hard particles, even in electromagnetism, you greatly decohere the S matrix element when you trace over the soft quanta which are produced. Now, I want to say again that I'm not giving an algorithm here for computing what the C's are. Computing what the C's are, so to solve the information puzzle, maybe you don't have to give a number for all the C's, but you have to understand how to compute them in principle. Like for a burning lump of coal, we could imagine how we could put it on a computer and compute the radiation exactly. Here we don't have a proposal, a dynamical proposal for computing what all the C's are. But this picture fits in beautifully with the work I've been doing on soft hair with Stephen and Malcolm. And so one will have to go into the details of the evaporation process, understand more what the implications of how a black hole carries these charges, what the implications of that are for the evaporation process, and that enterprise is in process as we speak. So in conclusion, we've, over the last 30 years, we've thought a lot about ultraviolet of quantum gravity, and there's all kinds of fantastic, beautiful things, interesting things that can happen in the ultraviolet of quantum gravity. But also the infrared of quantum gravity is extremely rich, much richer than we once thought, and has already yielded some surprises in the last few years, and we are hoping for more. Thank you very much.
Questions?
When you last came to visit us, at least when I was here, you gave a beautiful colloquium, and it mainly focused on the QED case, or the electromagnetic case, and it put me in mind of remarks of Roger Penrose, which geometrize what you said, I think, and that is the following. Really, if you're looking at the action of the conformal group on conformally compactified Minkowski space, you should identify scri plus and scri minus. And that's very clear from various geometrical constructions. And that means, since it's not simply connected, that you have non-trivial bundles. You have to, the fields are sections of non-trivial bundles, which is precisely your antipodal map transformation. And moreover, because it's not simply connected, you have flat connections with non-trivial holonomy, and that seems to be very much how you're describing the charges. So I think, I've never liked the S matrix, I should say, partly because we used to go in for it here and it was a dead end, but it seems to me that there could be a different way of formulating these problems for, certainly for electromagnetism, and I suspect also Yang-Mills. Certainly if they're pure Yang-Mills and pure electromagnetism, which would somehow eliminate even the mention. It's a bit like Michaelis's viewpoint. You would not even mention the S matrix or soft quanta. You'd be dealing with a regular field theory on a compact space with peculiar identifications. And I believe that strongly because if you ask people like Michaelis and Madame Choquet how they prove Yang-Mills classically exists, they lift it onto precisely the same space. They have a compact cross-section, and so they can use all their theorems of functional analysis. So it may be that this picture that Roger gave us in this particular case, well, Roger's aware of this. This is what is called in the trade the Gauguin discontinuity. But maybe we shouldn't focus on scri plus and scri minus as separate things in this particular case, but rather the same place.
Yes, and there are many different directions and ways that one could go with that comment. But I do one thing that is, I'm just talking about one little corner here, but there is a picture which seems to be a very nice one, which does exactly what you want, which is to get rid of scri plus and scri minus, and just keep the sphere, the celestial sphere, and then the scattering is a kind of correlation function on that sphere, and that is the sphere, that is the most natural way to think of super rotations and how they act. But certainly, yes, Penrose did, I've had in the course of this investigation reasons to read some very old papers of Penrose, and it's amazing some of the things he knew a very long time ago. But he got some things wrong too, and I think the conformal compactification was too strong. The boundary conditions for the conformal compactification. Yeah, with gravity was too strong, and I think and it was really Christodoulou that made that crystal clear, and that was too strong, and that thinking about things in those terms caused us to miss a lot of interesting physics.
I think actually in view of time we have to move on because otherwise we're going to lose light track. Bhabha's looking at me approvingly. So I'm sure there are many questions, but let's thank Andy again.
Thank you.